Hi everyone, welcome to this video. I wanted to make a video to help you understand your mistakes during the mid-year exams. Just a quick note, something quite interesting, at least for me, is that the average mark for this test is half the average that was achieved by last year's students. And the one difference between this year's students and last year's students is last year we forced all students to use the online course, and to if they were not up to date with the online course, they were deregistered. This year we did not do that because a lot of students got deregistered. But one difference is this year, last year they got double the marks, and we had double the number of students that were still registered. So it does seem to help to keep students accountable. But also I do want to encourage you, if you do have the online course, to make use of it. It really does work, which is evident for me now in the marks for the students' results. Nevertheless, let's continue with this. Okay, we'll start with the multiple choice questions. First off, which of the following is not an example of an object in free fall? And an object in free fall is an object that experiences only gravitational force. So which object is only experiencing gravitational force? Well, first of all, or is not only experiencing gravitational force. A cannonball that's been shot from a cannon, it has been shot from the cannon, so there's no other force acting on it except it's falling down to the ground. Okay, you can, with something like a cannonball shot, you can ignore air resistance because of the size and the mass of the object, but yeah, definitely not. Definitely in free fall. A paper aeroplane in level flight. Well, a paper aeroplane in level flight is not just falling to the ground because it's in level flight, which means there's something keeping it from falling. And so it is falling but slowly gliding, which means there's a force underneath the wings. So this is definitely the object not in free fall. A satellite in orbit is in free fall. It's falling. It's just falling off the edge of the globed Earth continuously. It's continuously falling. That's why it's in orbit. But it's falling off the edge of the Earth the whole time, or the curb. The next one, peregrine falcon diving towards the earth to catch its prey. Yes, it's falling to the earth, so it's in free fall. A motorist slams on the brakes of his car to reduce his speed to avoid a collision. Which of the following statements, which of the following is true? Momentum is not conserved because it's not a closed system. That's true. It's not a closed system, so momentum is not conserved. Why is it not a closed system? Because there are brakes being applied. Second one, momentum is conserved because there are no external forces acting on it. Clearly that's not true. There is external forces, the pushing of the brakes. C, the impulse of the car is zero because the impulse of the car is zero because the car comes to a stop. Well, that's not true. An impulse is the change in momentum. So since this car comes to a stop, the impulse is not zero. The only time your impulse will be zero is if you are traveling at a constant velocity, because then there's no change in your momentum. The car does not have momentum because there's no collision. Of course a car has momentum. Anything with mass and velocity has momentum. Okay. 4 tanks are being evaluated to pump water 18 meters high to fill up a water tank with a constant flow of water. Okay, so here's now they ask which one of the above pumps is the most cost effective. How will we determine it? Well, I think this is actually one where you would have to do some calculations. So let me just open the program we use for calculations. Okay, here we go. So to do this calculation, it's fairly simple. Let's take any amount of water. It doesn't really matter. Cost effective will be, if it's cost effective for 1 minute, it will be cost effective, the most cost effective for 2 minutes. So it doesn't matter how long it is. So let's choose just any number. Let's go for 100 liters. So if I was going to, so let's say we take 100 liters and we're going to pump 100 liters up. So according to our table, the first one, 20, can do 20 liters per minute. So 100 liters will take 5 minutes, 20, 20, 20, 20, 20, and it will use 650 kilowatts. So it will use 650 kilowatts, which is joules per second. And so if I multiply that by 60, that's how much energy it will use per minute. And if I say that's per minute for 5 minutes, what answer do I get? So I get 650 times 60 times 5 is 195,000 joules of energy being used. Okay, the second one uses see there, second one is 900 watts, and it does 60 liters per minute. So if I have 900 joules used per second, I want to do 100 liters, so it's 100 liters per minute. So I'm going to divide by 60. I'm going to multiply by 60. So this divide by 60 is how many minutes it will take me. Multiply by 60 tells me how many seconds, or it converts that to minutes. Okay, and then finally this times this tells me how many minutes I'm going to use. Okay, that multiplies by 60 to get my rate into I should actually multiply this by 60. Multiply this by 60, and that tells me how much energy I'm using per minute. This tells me how many minutes I'll need. So I'll take that away, and then I get, what do I get? So I say 900 times 60. Okay, that gives me 54,000 joules per minute. And how many minutes am I running it to pump 100 liters? Okay, so times 100 divided by 60. Okay, and that gives me 90,000. So that's 90,000 joules. So we can already see that that this bigger motor uses less energy per minute. The next one is 100 liters per minute and 1,200 kilowatts. So that's 1,200 joules per second times 60 to convert it to minutes, and I do 100 liters per minute. So I'm just going to run it for 1 minute, and that would give me 1,200 times 60 is 72,000 joules. I'll use 72,000 joules. The final one is 2 kilowatt. So it's 2,000 joules per second that it runs on, times 60 to convert it to a minute. And this one can take 1.25, so 100 liters, but it can pump 125 liters. So, okay, that one seems on the face of it, well, it seems like the pattern is it gets less, but let's try it. 2,000 times 60 times 100 divided by 125. And that is 96,000, sure. 96,000. See? Yeah, 96,000 joules. So in fact, these two are both more economical than the big machine. So, but this one would be the most economical, number C. Okay, and the final question here, which heading is appropriate for the following diagram? Voltage to current. We know voltage and current is directly proportionate So this is supposed to be a straight line. Okay, so it's a straight line for any ohmic conductor. What is an ohmic conductor? Most resistors. An ideal battery, that's definitely not the relationship between current and voltage for a non-ideal battery. No, a non-ideal battery means it's got internal resistance that is got a normal straight line relationship between current and voltage. A non-ohmic conductor, yeah, that's exactly what it is. That doesn't follow Ohm's law, where this should be a straight line. So for a rheostat is simply a resistor that can change its resistance. So the answer is a non-ohmic conductor. Answer C.